So today I'm going to talk about non-visual BCIs. I only realized afterwards that this isn't a particularly useful name because we've talked about non-visual BCIs, like motor imagery-based BCIs. So really this is talking about non BCIs that don't use a visual stimulus as their primary category, but also requires some probing from a stimulus as sort of the control signal. So this would be some external exogenous based BCI. I was going to talk about hybrid BCIs as well, but I kind of realized that I've already played my hands on a lot of hybrid stuff because I want some guest speakers to talk about them. So I don't want to have a lot of redundancy. And this will be a slightly shorter lecture, and then I'll talk a little bit more about logistics for what the class is going to turn into starting next week. And yeah, I'll take some questions from there as well. But before we get started, does anybody have any questions? Oh, I see a chat question. Okay, quick question. How many EEG electrodes are on equipment provided? That's a good question. So there are 16 electrodes on the cap, but we only have access. Our amplifiers can only take in 8 channels. So if I go into Open BCI Shop, I'll give you guys the PDF of this as well, so you don't have to go through this process. But so we have this. This is the cap we have, and this is the amplifier we have. 8-channel Cyton. Then we have the all-in-one EEG electrode cap starter kit. So the cap has 16 electrodes on it, and I'm pretty sure one of these is the montage. There we go. So the ones that are highlighted in yellow are the electrodes we have to record from, and you can only choose 8 out of the subset. So one thing that I've recommended to groups who are they're trying to replicate an analysis or something, then I would say, choose your channels off of what the literature you have suggests. Or if you're trying to, you actually have a data set, you can say, okay, I want to replicate this, so, my analysis team is going to take this data set that has 128 electrodes, and we're going to run analyses to say, okay, if you can choose 8 only from the subset of the 16 we have allowed, what gives us the best performance? And then you can use that. So you can iteratively determine that. Otherwise, feel free to ask us which electrodes make sense. So for example, if you're recording ERPs like the P300, event-related negativity, pretty much any ERP, you're going to want midline electrodes, so FZ, CZ, and PZ. It's a good idea in general to record from either FP1 or FP2 because they can pick up blinks really well, so it's a good way of determining if a trial has a blink and then just rejecting it. If you're doing more motor imagery stuff, you definitely want some central electrodes, like definitely C3 and C4, but you probably want to throw T7 and T8 in there as well, and also probably F3, F4, P3, P4. So yeah, definitely we don't have infinite options, but it's pretty good actually. This is a very low density setup, but you can still get pretty good head coverage even with only a subset of 8 channels. And again, a lot of the stuff people want to do, you can do with just a single electrode in theory. You don't even need 8 of them. Like if you're doing SSVEP stuff, you could use O1 and O2, or you could just use either one, and it'll essentially be just as good. But yeah. And then one thing that I still have to hash out is how we'll deal with grounding and referencing, because they say this is an all-in-one electrode cap starter kit, but they actually don't give you everything you need because they don't give you a dedicated electrode to use for reference or for ground. So I'll have to figure out what the best way to do that is, because the choice of reference is non-trivial depending on what you're recording, and ground is trivial, doesn't matter. Anyway, that's that. Good question, though. I've had other students ask that as well. Cool. Oh, I want my presenter view. Yeah, feel free to throw other things in chat. If I notice that it's more logistics, I might just wait to talk about it until the end of the lecture, but I will get to it. And if it's related to content, I'll respond to it right away. Okay, so non-visual BCIs, aka also non-imagined BCIs. So I'm not going to talk about like motor imagery or anything. Okay, so there's this really interesting paper from the BCI Society. It's a journal or a conference paper, so really it was a panel of experts who have done BCI work on actual populations that need BCIs. And they were talking specifically about the number of publications using P300 BCIs and sort of the pragmatics of, what's the state of the art for P3B BCIs on populations who actually need them. And this is, I sort of want to motivate why we're talking about non-visual BCIs because of these populations. So I've said it before and I'll say it again. Most BCI papers are recorded on healthy subjects, probably like, if I had to just make up a number, I would say honestly like 99% of all BCI papers are either recorded from healthy subjects or they're machine learning algorithm-based papers or signal processing-based papers working on data sets collected from healthy subjects. Pretty much nobody is actually recording from people who are in, who have ALS or are locked in, at least in the non-invasive world. In the invasive world, you get more people who have some sort of disability because that tends to be the reason why they have an invasive BCI, or they have some epilepsy and they're testing things for, if somebody was in a similar state and had a similar configuration of invasive electrodes. But there are legitimate differences between somebody who's in a locked-in state and a healthy person. So this panel talked about a lot of participants who had ALS. And ALS is a very interesting disease because the brain is actually becoming demyelinated over time. So it's not just a disability that causes you to lose control of your extremities and your immediate muscles, but it's also going to be directly affecting the neural pathways. They are actually changing over time. So there should hopefully be some intuition there that systems that work on healthy people who have, fully myelinated axons and dendrites and stuff are going to have different signals than people whose brains are slowly deteriorating. Like the signals visibly look different, and that has a difference in, how you're going to be classifying these signals if you're using it as a control signal. The other thing is that as the diseases like ALS progress, participants start losing their vision, so their vision does become impaired. And there's also real pragmatic differences with how visual stimuli are presented in patients versus regular participants. So we often see, like the P300 grid matrix where you have a bunch of stimuli flashing pretty quickly. Although you don't necessarily need eye movements to lock into those, and you can just use, you can guide your attention rather than your actual foveation. These designs are still uncomfortable for the participants. So having all these flashing, rapid stimuli doesn't feel pleasant to look at. And so the systems are less usable, and they're also just not comfortable for the people who actually need to use them. So one thing that you could do is, okay, maybe rather than doing these rapid visual things, we slow it down, we do more serialized presentations rather than probing in parallel. But even then, you still have this very real problem that the auditory pathway starts degrading. So it makes sense to think about, okay, are there any other ways that we can present these stimuli for these participants? And of course, when participants get fully locked in, completely locked in, it's very difficult to guide their eyes towards a particular part of the screen, and it's not clear at that point if their visual pathway is even working. Now, this can be true for other sensory modalities as well, but it makes sense to move away from vision if there's something else that's more intuitive to these participants over time. So in this panel discussion, they had this list of, I'm pretty sure that this is, at least to the author's best knowledge, and this was in 2011. These were all of the BCI, non-invasive P300 BCIs that were created for actual patients. And on this list, 2 of them used auditory stimuli, and the rest of them were visual. Now you'll see from this graph right away that the visual stimuli perform a lot better in terms of their online results, in terms of their actual online classification. So the lowest numbers in this are the audio scenario in Sellers and Donchin and the pure audio in Kubler. So there's definitely some trick to using audio stimuli that hasn't really been figured out or hadn't been figured out. And I'd like to talk a little bit about sort of how these stimuli are designed, how these tasks are designed to use non-visual stimuli, and maybe what are some things that we could do in the future. So in Sellers and Donchin, they made a 4-class BCI, and there were 4 commands, which were yes, no, pass, and end. And participants completed 3 different modalities. So they had audio only, visual only, or audio and visual stimuli. What's interesting about this is that they didn't actually want to have more than 2 classes, yes or no, but because if you have 2 classes, it's just 50% whether or not you detect it. So, the P300 is binary. You're going to tell if something's a target or a non-target, and you get the most benefit from the target stimulus being low probability. Having a 50% task condition is not necessarily the best idea. It also makes it hard to evaluate your classifier's performance. So instead, they chose 4 classes. That way, the target is always going to have a probability of 25% of showing up, which is good for the P300. And it also makes the chance level of detecting the signal correct 25%. So the more classes you have, the lower your chance rate is. So if you have a classifier that is able to detect a signal really well, like let's say you had something that can perfectly detect the P300, you can arbitrarily increase the number of classes and get better overall speller performance just because you have more classes. So that's something to keep in mind, assuming that the P300 is detected equally in all of these cases. But that's what they did. The task overall was they were presented with questions that were unambiguously yes or no. So the only viable targets in this case were yes or no. And they recorded from 3 control participants who were just healthy subjects, and then 3 ALS participants of different severities. And in the paper, they talk about the specifics of every individual's condition. So some people are able to, still move their limbs. Some people are able to walk. Some people can walk, but it really hurts, and they prefer to use a wheelchair. Stuff like this. This is very common to get details on each individual subject within these papers. So here are some examples from the healthy participants. So these are the non-ALS participants. And the way that they actually chunked up the data was the same for each of both the control subjects and the ALS subjects. So they had these epochs from 100 milliseconds to 1,000 milliseconds, which they then did some windowed meaning, and they took a subset of channels, and they passed it into stepwise linear discriminant analysis, which is very similar to LDA that we talked about already. It should be worth noting that LDA by default doesn't really care about the temporal organization of your signals. So we have these time sequences within a window of our epoch that we're sort of taking these windowed means of. Essentially, we're just downsampling them. And you can see these trends, right? You can sort of, you can imagine if you look at the, participant 1 visual, that you'd see this really nice trend, even downsampled of it's sort of at 0, then it goes super positive, then it goes back to 0, then it goes kind of negative. But LDA doesn't care about that organization. You could sample all of the time points, and it would perform just as well. It doesn't know the organization. Stepwise linear discriminant analysis cares about that slightly more, because if I remember the algorithm correctly, you feed points into it sequentially until you get some sort of classification performance. So because of that, you would get, you would get a different set of results from shuffling the points and feeding those in sequentially than you would from having all of the points and then feeding them sequentially until you get enough classification. So each subject in each scenario is going to have a slightly different number of points that are actually being used for the discrimination. There are problems with SWA. There's a group that, I think in like 2019, they came up with a temporal-based linear discriminant analysis to sort of encode some of this time information. And it's honestly something that more people should be doing and testing, including myself. But a lot of the times you get really stuck in your ways when you're doing this type of stuff, and you don't want to twist too many knobs because you just, you know the math behind something, and you don't necessarily want to throw another wrench into the works. But it is something more people need to do. Anyway, here are the healthy participants. Their signals are looking pretty good. Participant 2 is weirdly getting a pretty strong P300 both from targets and non-targets. So it's not particularly discriminable. This might be due to not understanding task constraints correctly. Participant 1, though, we see, and actually in all of them, you can see that there is a difference between the auditory and visual tasks. So at session 1, for participant 3, for example, there's like no real noticeable P3, or maybe just like a really delayed P3, if anything, in the auditory. And there's more of that, like the amplitude of that signal is definitely increased in visual, and then it goes down in visual and audio, which is interesting. But in general, the ERPs are not very clear from the auditory stimuli. But these, this could be showing that the task itself is not particularly clear to the participants, or maybe there's something that they needed to change with the volume of the auditory presentation or something. The participant isn't as responsive to the timbre of the voice that's saying it. There's a lot of parameters to this. And here are the ALS participants. So participant 1 actually has a pretty clear signal. They have a bit of a delayed P3, which is not uncommon. So, we talk a lot about ERPs having, or these components having these very signature time elicitations and also spatial, sort of like where they are topographically. But these variables change with age, they change with condition. So for example, as people get older, the onset of the P3 gets delayed. As you can imagine, if your processing pathways are slower because your axons and everything else is losing white matter, gray matter even, you can imagine that these responses are going to be delayed and they're going to be a little noisier. And in participant 2, we sort of see something that looks like a pretty strong, peaky P300 on visual, but in auditory, it's a lot more jagged. This means that it's probably more variable, or the signal is just not as strong. And then participant 3 has very difficult data to discriminate. It seems like it gets easier by the time you get to session 10, but at session 1, a classifier and a person would have a hard time distinguishing which class these signatures belong to. And remember that these are averages, so that's every trial in the category being averaged together. As you can imagine, it's even harder to distinguish these different classes at the single trial level. But yeah, so let's go back to that chart. So this is the first one. So you can see that the classification rate for visual was 69%. Auditory was 61%, which is actually still pretty good. That's significantly above chance, which is at 25%. And the audio-visual does slightly better than auditory, but it still does worse than just visual alone. And that might be not intuitive. You'd think, okay, you have these multiple streams of information. Shouldn't that always give us more information? But there is a lot of... It's not clear in all contexts how the overlap of multimodal responses look, because, if you're getting, let's say you're getting a P300 from both the auditory cortex and the visual cortex processing pathways, those aren't going to necessarily sum up to make a larger peak. They might actually end up blurring the signal over time. And because, for example, if you have, let's see if I can draw on the screen. So if you have if you have a visual P3 where you have something like this, okay, and then you have an auditory P3, which might happen a little earlier actually, something like that, and then you take the average of these points, this peak is going to go down because this point is less positive, for example. This peak is going to go down because this point is less positive. You see what I'm saying? So because you have these individual, because you're getting this information summated in real time within the user's brain. This isn't even like an average that we're doing offline. This is just these components are going to be averaged by the time they get to our electrodes. The individual components might actually get attenuated. Now, if you had the opposite, like if I took this auditory stream and pushed it over by like 100 milliseconds, then you would have this additive property instead of this destructive property where the signals actually end up combining they might sum up and make a much larger signal that's easier to discriminate. But it depends on the context. So in a lot of multimodal tasks, it's not exactly clear what's happening at certain stages. When we're making BCIs for people who are in ALS, for example, the specifics of what's happening matters a lot less, and the usability of the system matters a lot more. So it turns much less into a scientific problem and much more into an engineering problem at the pragmatic stage, right? So like, for example, if somebody came up to me today and wrote me an email and said, hey, you're a BCI researcher, my husband of 50 years has become locked in, can you please make him a BCI? I would say yes, and I wouldn't make anything new. I would literally just start from one of the designs that already exists with a pretty broad electrode array, and I would just hack it together until it worked, obviously using past work and using the knowledge that I have, but I wouldn't try to invent something new unless I had to. I would just iterate through everything that exists until you find something that works. I mean, it really does turn into a pure engineering problem at that stage. Because at the end of the day, you're trying to give these people who have very little ability to communicate some ability to communicate. So you can't be playing around with all this fancy stuff when you actually have a participant that you're trying to make a system for. That's also part of the reason why these papers are more rare. Most of the time when you're developing a new system, you're going to do it on healthy subjects because it's just easier to develop that system. And then you can state in your paper, like everybody does, like, okay, we'd eventually like to test this on ALS patients. But the problem is, it's not clear a lot of the times if these systems that work for healthy patients would even have a chance of working for an ALS patient. So sort of turning it more into an engineering problem starts making more sense. But of course, it's good to have the literature to base things off of. And again, I will point out that P3 spellers started originally for people who were in these debilitating states, right? So Farwell and Donchin made it for a person who became quadriplegic or locked in, So it wasn't like they're like, hey, let's make this BCI speller on healthy people and then test it on somebody else. It's like, no, they're making it for that person. They had to beta test it first on healthy subjects, and then they immediately applied it to the person they were building the system for. So. Okay. So this is the other paper that was mentioned in that table. So in this case, what did I want from this? We assume that at least in most patients, auditory and somatosensory pathways remain functional, offering a possible alternative for stimulus and feedback presentation for BCI control. So building off that same logic of, okay, a lot of ALS patients and people in similar conditions lose the ability to process visual stimuli because they lose control of their eyes, yada, yada. So let's try to build a auditory-based BCI. They were inspired by the classic grid speller, and in this case, they say that they just used auditory stimuli, but they did have this visual aid for participants. And what they did is, rather than spelling out individual characters one by one, they mapped, every row and every column has a number. And so in this case, the rows are numbers 1 through 5, and columns are numbers 6 through 10. And just like in the visual matrix speller where they would flash entire rows and entire columns, they would, in this case, give you the sound cue of the number of each row or column. So it'd go 1, 7, 4, 10, so on and so forth. And exactly the same way that you would probe to see which letter was correct in the visual grid speller, you look for the intersection of where the highest row classification was and the highest column classification was, and pick that as your letter. So yeah, this is not, maybe this isn't the most intuitive design to you. It makes sense why they did this, because they're building it off of the most well-known P3 speller at the time and still now. But this does require some, I would imagine that this would be very hard for participants to keep in mind if they didn't have the visual cue. So I don't think it's necessarily fair to say that this is a pure auditory BCI, because the performance is going to be dependent on how well the participant remembers which numbers map on to which subset of letters. And they also don't do that well in their classification anyway. And they actually quantified their performance in 2 different ways. They have the selection accuracy, which is this is the ability for the row and column to be correctly classified. So this is choosing a correct letter, essentially. And then they have the classification accuracy. So selection accuracy is actually selecting the correct letter. Classification accuracy is selecting just a correct row or column. So this is how well does the system detect the P300 out of, in this case it's 1 in 5 chance. And the selection accuracy is how well does the combination of the 2 1 in 5 probabilities go in to select one of 25 letters. They got rid of Z, by the way. That's the, if you were wondering how they were able to fit everything in a 5x5, they just said Z, not important, which is, fair most of the time. So this is the results. They ended up having different subjects spell a different number of words, which if you've ever actually done these real-time BCIs is very relatable, because it can take a different amount of time to collect calibration data for each subject, and it can take a different amount of time to actually prepare the cap to start collecting data for each subject, which students who end up collecting data in the lab for this class will realize. So in this case, we have the target letter. So yeah, the important thing here is target letter and then the letter that was spelled. And so for example, if we look at the first subject, they're trying to spell winter. And so for assessing the selection accuracy, okay, the W is correct. The J is wrong, but it's honestly not super far off. The N is correct, J is off, B is off, S is off. So in this case, we have 1, 2, 3, 4, 5, 6. The two of the 6 letters were spelled correctly. And then they tried spelling winter again, and then we only got 1 of the letters spelled correctly. And so that's how we determine the selection accuracy. The classification accuracy, again, is just can we select the correct row or column. And yeah, if you've ever made a BCI that is a little off, like the BCI system that I made, seeing these jumbled letters is not uncommon. One thing that we can use to supplement this is to use language models. So what I use in my study is I have a probabilistic, I'm keeping track of what the most probable letter is at any given time. And I can use the end weights of these letters to feed them into sort of like an autocorrect, where every word is not like, every letter that you select is not just this is the letter we selected. It's just the highest probability letter that's selected, but it belongs to a distribution of every other letter's probability. And what we did was we built the language model that took all of these probabilities into account and used them to sort of autocorrect the final word. And if you use that, you're able to correctly spell words slightly better. In my case, I used a very extensive corpus, and really what you want to do is use a very restricted corpus. And especially when you're designing a system for somebody who's in a state like this, you don't need to have every possible word be something they can spell. It just needs to be pretty simple. And you can calibrate things on a much smaller corpus, and you can tell participants which words are allowed, and you can end up getting better spelling accuracy with a combination of using the BCI stimulation and a language model. So in this case, like at least the first participant would have benefit from this because there's probably not that many words of this length that could be autocorrected to anything else but winter. The other thing, and this is not talked about as much in copy spelling, so this type of design is called copy spelling. The participant is given a word that they're trying to spell, and so the experimenter knows the length of that word. So you don't have the participant also trying to guess an additional signal, which is stop spelling. You're just always aware of the actual sequence length, which is a much easier problem than if you have to have the participant guess, like also respond to should they end or not. So just putting that out there. The copy spelling, very achievable. Real spelling, much harder in synchronous systems like this. Much easier to do in SSVPs, but for the same reason that ALS participants don't like or can't use visual stimuli, we can't use SSVPs. But some of you might be thinking, okay, I know SSVP is steady state visual evoked potential. Could we have like steady state auditory evoked potentials or steady state, I don't know, olfactory evoked potentials? And the answer is yes. Yes, you can. So I didn't bring up an SSAEP, but I am going to talk about an SSSEP, or also called SSSMEP, which is steady state somatosensory evoked potential. So in this case, the study we're going to talk about used these transducers to pulse a signal at a particular frequency. And just like in the steady state visual evoked potentials where we can distinguish if somebody's looking at like 8 hertz or 15 hertz just by their brain's response to those frequencies, we can use these vibrations on a person's fingers and have them, like, let's say you have, I'll just show you the figure. I love this figure so much. It's so funny. It's just like this little head with this giant hand. I think it's hilarious. But you have the participants with their index fingers on 2 different transducers that are vibrating at these different frequencies. And you can just tell the participant to focus on the left or the right. So imagine in this case something very similar to a motor imagery paradigm where you're trying to move a cursor left or a cursor right, and rather than doing motor imagery for that, you just focus on the vibration on your left hand or the vibration on your right hand. So they use 2 different frequencies for this. FT2 is just 5 hertz below FT1, which is the first frequency, and they looked for this frequency in every individual separately. So they used this sweeping approach to, they probed from 17 hertz to 35 hertz in 2 hertz steps, and they recorded from every subject their response to these different frequencies, and they picked the one that resonated the best, so the one that you'd get the most power from consistently. So this list is here. Oh, also, I'm pretty sure this study was on healthy subjects, by the way. Just keep that in mind. And I only say that because people who have ALS might actually have degraded somatosensory inputs at the latest stages. But yeah, so everybody was in this 25 plus hertz range, which is interesting. So between 25 and 31 hertz is where they were having this maximal response. And the way that they stimulated the fingers were with these transducers, essentially just little speakers that they amplified and had the participants' fingers directly over. They also had white noise in the background so that the actual sound of the transducer wasn't affecting the classification. Because you can imagine that it might be a little, honestly, these tones are probably not audible. I mean, 25 hertz is like unbelievably bass pitched, like only a super good subwoofer would be able to accurately pump that out so that you could feel it in your bones. But a little transducer like this, even amplified, it's probably not going to be that loud, but the harmonics from the actual plastic resonating and chattering would produce a sound that it might be given some, I don't know, there might be some additional cost to that in the sensory processing pathway, so they said, okay, let's get rid of that, let's just use white noise to sort of cancel out this additional processing. So we can just focus on the response to the vibrations. So I've modified this figure because it had some information that was not super useful, at least for what we're talking about. where they had subjects come in on multiple different days. Day 1 is not shown on here because essentially what they did is, for day 2, they trained their data on day 1. For day 3, they trained their data on either day 2 or day 1, depending on the quality of the signals from the previous day, and so on and so forth. This comes from the necessity to record calibration data for our participants because EEG is non-stationary, so signal is going to change over time. And this actually ends up being a harder problem than what we get in a normal study because usually we're collecting the training data and testing data right there, right then. So we're sort of trying to maximize the relative stationarity within a single recording session. But studies like this, which are multi-sessions, are sort of they're not getting any favors by that. But it's also more pragmatic because you wouldn't necessarily want to have to collect calibration data the first time a participant wakes up every day, or maybe like 4 times a day in order to get a system to work. So if you can make a system that can work on the previous day's recordings, then it'll end up being more usable over time. And then they also looked at the offline, which I think they changed the parameters in terms of the sliding windows that they had access to offline, and then their actual online, which was calibrated on the previous data and then was actually working in real time. And they were able to get, at least for subject 1, they got pretty good accuracy. For the other subjects, it's still above chance, but like subject 2, the online classification is not that much better than chance, which is just 50% in this case. So definitely a limited case study, but shows that in theory you could make these somatosensory-based BCIs to use as control signals.